and here. Okay, so guys, this is the way questions work. We are going to move together. If we are not immediately answering your question, don't tune out, because we are going to be talking about stuff that you're going to benefit from whether you got the question right or not. We will answer all of your questions, but we're going to do this as a group. And guys, this is going to be wildly conversational. So as we get into this, there's two things that you need to understand. Number one is this: I am not the smartest person in this room. You guys understand that, right? I am not the smartest person in this room. There are people in this room that blow me away in terms of their ability to reason, blow me away in terms of their ability to problem solve. The only advantage that I have over most of you is, one, I've got a degree in chemistry, and two, I've seen these problems before. So seriously, guys, you got to get over this idea that teacher is the sage on the stage and I'm just here to deposit wisdom. So guys, don't be frustrated, or even if I go, I don't know the answer, let's figure this out together. I'm not threatened by that. And to be honest with you, it's my favorite part of the day because I get to learn as well. So guys, understand, I'm not the smartest guy in the room. And also understand, we may find some mistakes in the key. I made up this key. It's 3 or 4 years old now, so it's pretty tried and tested. But guys, I would suspect some of you tried to also look at the answers in the back of the book. Don't use these, please. I actually know the girl that wrote these. Her name is Roxy. She was going to be a student. She was going to be a peer of mine in graduate school. She's super bright. But guys, you don't know this about me. I actually was the person that wrote the answers to the end of chapter questions, not for a chemistry book, but for an educational psychology book when I was a graduate student. I know the amount of work that goes into writing these things, and I'll be honest with you, I did them late at night when I was tired and grumpy, and a lot of the answers are wrong. Same thing is true for Roxy when she did these. Some of these answers are wrong. So when in doubt, trust my answers because they're better, okay? So, guys, with that said, what questions do you have? We're going to identify these by number, and guys, I don't know why this drives me nuts. Don't call this 3.3. We all know what chapter we're in. We're just going to call this 3A. So Robbie, get us started. What do you want to talk about?
So I guess this is more like the next question.
Just tell us the number. What question?
On question 5.
Perfect.
I just had, I kind of forgot with significant figures in addition.
Yes.
Because our the periodic table we're using,
Mm-hmm.
I use testers, right?
Yeah. Yeah.
So like when you're adding 24.02, 5.04, 14.01, and 13.00, are you restricted by the 5.04?
That's a great question. Yeah.
Or are you still keeping the 4?
You want to have the significant digit talk. Is that right? Let's have the significant digit talk. So guys, here's the deal. 4 years ago, they removed any requirements on the AP chemistry test to adhere to significant digits. Any number that you wrote down, so long as it was numerically correct, they accepted. People freaked out. AP teachers, college professors, everybody wigged out. So significant digits are back. But here's the rule for significant digits. Ready? You have to be within one significant digit of the correct answer. So you can be one above or one below. We're going to play with that later, because when we really start studying for the AP test, what we're going to do is we're going to say always put 3 significant digits, because it'll always be between 2 and 4 and we'll never be wrong. But with that said, what about when you're finding molar masses? And this is the answer. Always 1 decimal place, more if necessary. So what does that mean? And what it means is that when we find molar masses, we're always going to go to 1 decimal place. But, and this isn't the case, but let's do this. What if our starting point in number C, letter C, was 3.17253 moles? Well, now this is 6 significant digits. And if this is 6 significant digits, this needs to be 6 significant digits as well, if that's possible. And frankly, it's not because we don't have enough information. But the bottom line is this. We will always go 1 decimal place. Then we will, as much as we can, not allow our masses to limit significant digits in any further math. So always 1 decimal place, more if needed. And you're absolutely fine. You can always go more, just don't go less. Okay, guys, go ahead. Okay. Yeah, good question. So here's the deal, if I may. So Jason's question is, are we using this or are we using that? And guys, the answer is this. This is the one that you will get on the AP test. This is the one that they would say contains all the information that you need to be successful on the AP test. With that said, we can't use this to do the assignment that we've been working on in lab, right? So there will be times that we have to grab this periodic table simply because there's stuff there we need, because you don't have to memorize the electronegativities, but you need to know the trends. So use this, and then if you need to grab that for some weird reason, we'll have it sort of in reserve. Just a second, you had 2 questions.
The same one is kind of what Robbie was saying.
Yeah.
When you are finding one mass,
Mm-hmm.
when you take a look at each of them, do you go 1 decimal? How much significant figures would you use?
Yeah, so what I will typically do is I'll go 1 decimal place on all of them, but I got to be honest with you, I don't look many of them up. I know sulfur's 32, I know carbon's 12, I know oxygen's 16, I know sodium's 35.5. Some of them I memorize the decimals, some of them I don't. If you're in the ballpark, you're going to be okay. Yeah, and I know that that feels weird, but if you're within 1 significant digit, which would then always go 1 decimal place, and then we'll be fine from there. Is that okay? Go ahead.
So I found, I can't remember like specific problems, but
Okay.
a couple times in the assignment, I was trying to put together molecules that I'm used to using the charges from that periodic table.
Okay.
And so is it okay for me to just grab that periodic table with the charges, or do I need to find a way to like memorize it?
No, that's a good question. So you said 2 maybe conflicting things. So when you're putting atoms together to make molecules or salts, right? Because charges are salts, oxidation numbers are molecules, and those are a little different. But in either case, what you're really looking for are those oxidation numbers, right? And here's the trick. You will not have those on the AP test, which means you need to be able to figure out what they are. But with that said, remember that we do know trends. And guys, I don't know if you're all a part of this conversation. Oh gosh, I almost didn't make it. Okay. I'm still really sore from CrossFit. So guys, the simplification goes like this. All of these go +1, all of these go +2, all of these go +3, then these guys can go plus or -4, then -3, -2, -1, and then obviously the noble gases. So if you understand that general trend, you're 90% of the way there. And then the other thing you can do is you can look for contextual clues. Like it might ask you copper 2 chloride. Well, the 2 tells you the charge of the copper. Because remember, these guys are tricky because the transition metals can have multiple oxidation states. But 90% of the time, the formulas can be arrived at, I don't know how to say that well, can be figured out based upon the charges, based upon the trends. If that's not the case, then there's probably something in the problem you can use as a clue. Okay. So guys, this is wonderful because you're asking big, broad, high-level questions. And this is exactly what I expected today as we're picking off big ideas, and this is wonderful. Go ahead.
So 35A.
Okay.
So it gave us a picture of a
Yeah, right. Yeah,
Is there a right or wrong way
that's a good question.
to put the order?
Yeah, let's look at it. So guys, looking at 35A, which is in the upper right-hand corner of 105, is there a right and wrong way to do that? And the answer is yes. But the reality of it is right now you don't know what that is. Okay, so looking there on page 105, guys, for now, if you strung that together any old way you could, that's fine. I think, Addie, for now, maybe a good way to think about this is work left to right. So you might go NH3, CH2, C, maybe you put O2, and that would be just fine. Yeah, understand that as we get into this more deeply, we'll talk about what's called organic nomenclature, which is the naming of organic things. Organic means contains carbon. We'll get there. For now, just put it in order. Yeah, that's fine. So, guys, let's do this. Are we good on high-level questions? Can we talk about specific problems now? Did that fit into your plan?
Yeah.
Go ahead. Okay. Just what on earth? Okay, so let's read the question. So number 3 says the following diagram. So the one down below, the following diagram represents a collection of elements formed by a decomposition reaction. It says if the blue spheres represent nitrogen and the red ones oxygen, what is the empirical formula of the original compound? Are we okay with that one? So we're talking ratios, right? And so that should be... Then letter B. It says, could you draw a diagram? What if you just put no? Then you don't have to worry. Could I? No, I can't. And then you're done. And it's true because you can't. It's not a very well phrased question. Could you draw a diagram representing the molecules of the compound that had been decomposed? Why or why not? And actually, frankly, the answer is no. But let's talk about why. So the answer is this. You may remember when we talked about empirical formulas, we talked about the idea of sugars, right? And the 2 sugars that we looked at were C6H12O6 and then C11H22O11. And I don't even remember the names of the sugars, but it doesn't matter. These are both sugars. So the trick is this. In order to figure out an empirical formula, literally what they do is they take this thing and they rip it apart into its component atoms, and then they count. And when you count, when you rip this apart, you get a 1 to 2 to 1 ratio of carbon to hydrogen to oxygen. Well, if you take this thing and rip it apart, you're still going to get a 1 to 2 to 1 ratio carbon, hydrogen to oxygen. And that's why you can't tell that an empirical formula simply tells you the ratios, but it doesn't tell you directly what the molecule originally looked like, because anything with this 1 to 2 to 1 ratio is going to fall apart into CH2O. Makes for an interesting follow-up question. What other bit of information do we need to know in order to be able to figure out its molecular formula? The molecular mass. If we know the molecular mass, then we can do that additional step, and we're going to do that in lab. Does that make sense? Okay, what else, y'all? Other questions? Go ahead. Is that the very last one? Oh, okay. 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 Josh, you ready for this? Here we go. Okay, guys, number 57. You may or may not remember, and frankly, if you had Miss Call, and guys, understand, I will be talking about Miss Call because she's the other person that does this with you last year, and you guys know she's amazing. But it doesn't mean that our classes were always the same. Same big ideas, maybe different examples. And to be honest with you, as you're finding out, I love to babble about stuff. Miss Call's very much more focused than I am. I tend to chase butterflies while she's like a laser. So, guys, with that said, looking at question number 57, if you allow your eye to scan through question number 57 with me, is it the one that's talking, is it washing soda?
Yeah.
Okay. And guys, it says something interesting about washing soda. It tells you that washing soda, is it sodium carbonate? What is it? Sodium? Okay. So guys, it tells you this. It tells you that washing soda is sodium carbonate. Ionic or covalent? Is this a salt or a molecule? It is a salt. And guys, as a salt, it exists in a lattice. Now here's the idea. And guys, remember, chapter 3 is weird because it's a lot of review. So the idea is this. This is table salt. Sodiums and chlorines, right? Chlorides. But guys, and you don't need to know the exact structure of the lattice. We used to have to teach lattice structures in here, and they got rid of it a couple of years ago. But guys, this is also what washing soda looks like. The difference is this. The little guys, the gray guys, are the calciums, and then the big guys, the green guys, are the carbonates. So for this to actually look right, this big green guy would have to be a carbon with 3 oxygens bonded around it in a trigonal planar structure. But the model still holds true. The other thing that would be different is there'd have to be twice as many gray guys as green guys. But fundamentally, this is what a crystal lattice looks like. You okay? Okay. Now, in this question, it mentions the idea of a hydrated crystal. What does that mean? Well, guys, let me show you a different hydrated crystal. This we actually used multiple times in class last year. This is copper 2 sulfate. I labeled it CuSO4. Remember we used this in the mole station a couple times? And I labeled it copper 2 sulfate. Because here's the trick. This is not copper 2 sulfate. This is actually what is called copper 2 sulfate pentahydrate. Guys, this is a hydrated crystal. Trapped inside this crystal is a bamboozle of water molecules. As a matter of fact, for every copper sulfate, there are 5 water molecules trapped inside this crystal. But it's not wet. Guys, clearly this is bone stinking dry because the water molecules are trapped inside the crystal. Now here's the thing that's cool. You melt this, the crystal breaks down, just like ice melting. When you melt it, the crystal breaks down and the water boils away. That's what this question is about. So guys, it actually looks kind of like this. If you could look down inside the washing soda, really this is what it looks like. There are water molecules all trapped up inside of this crystal. Like so. Now the trick is this. It doesn't feel wet because the molecules are trapped inside the crystal. But if we heat this up, the crystal collapses and the water boils away. Now imagine this. Let's use round numbers. Imagine if we started with a pound of this, and then we heated it up and let it melt, and then once it cooled, we weighed it again. Would it weigh more or less? Why less? The water boiled away. How could we figure out how much water boiled away? Weigh it before and after. And then, guys, at that point, it becomes an empirical formula problem. And that's what is happening here. We have this hydrate that weighs about 2.5 grams. When you boil it and get rid, well, you melt it and boil off the water, it weighs 0.948 grams. Subtracting those tells us that about 1.5 grams of water went away. So now here's what we know. We know that the water weighs this, and we know that the unhydrated sodium carbonate weighs that. So then, guys, what we do is we take these two masses, convert to moles, divide by the smallest number of moles, and that gives us the coefficients for the empirical formula. The only difference is we write it like this, and instead of putting the 10 down there, we put it in front because that's the way that we write hydrated crystals. What do you think? Good? Okay. What else, y'all? Go ahead, Caleb.
I was getting weird numbers on
Let's talk. So guys, number 79. Number 79 looks like this, but I don't want to look at this question first. But I will tell you this. Guys, number 79 is well within the scope of reason of something that you might see on the AP test. The reason is because it is not simply just mathematical, it is logical. And they love to ask these kinds of questions. But guys, before we get into this, what I'd like to do is I'd like to turn your attention. Where'd it go? I'd like to turn your attention to number 63. Would you go there with me? So guys, number 63 goes like this. We have 0.5 grams of aluminum hydroxide. And basically what question number 63 is asking you is if you start with 0.5 gram of aluminum hydroxide, part B, how much HCl does it take to react with it? Then, and unfortunately this is on the next page, part C, if you've got 0.5 gram of aluminum hydroxide, how much of this product can you make? And if you've got 0.5 gram of aluminum hydroxide, how much of this product can you make? So by doing calculations A, B, and C, you can then figure out, by doing those calculations, you can then figure out the masses of all the reactants and products. So we know that this one weighs 0.5, we know this one weighs 0.702, and on the next page we figured out the masses of the products. And then guys, part D gets a little magic. What happened when you added these up and added those up? They're the same. Why? Law of conservation of mass. Guys, the only difference between this and question number 79 is they don't tell you which reactant to start with. In this one, they tell you start with 0.5 gram of aluminum hydroxide. In number 79, they don't tell you which reactant to start with. So which reactant do we start with? The limiting reactant. So the first calculation in number 79 is figure out which one is the limiting reactant. It turns out from the math that silver nitrate is the limiting reactant. That then means, because remember guys, the question is, how much of this stuff remains when the reaction is over? And by definition, the limiting reactant is what you run out of first, it gone. You use up all 5 grams. Now guys, the rest of this problem is exactly like the previous problem we just looked at. Now we're going to do a bunch of math. We're going to do this 3 times. All 3 times we are going to start with our limiting reactant. The first thing that we're going to calculate is, where did it go? How much sodium carbonate is needed to react with all of that silver nitrate. And it turns out that the answer is 1.6 grams. So 1.6 grams of the sodium carbonate gets reacted up. But guys, it told us initially that we started with 3.5 grams. So if you start with 3.5 grams, and if you use up 1.6 grams, how much is left over? Subtract. And then guys, once you figured that out, these last 2 are just like the previous problem, where you're just calculating how much of the products gets produced. Does that make sense? You okay? Caleb, what do you think? Which part didn't you like?
Well, I was using
Okay. Yeah, so use our answers. But guys, I have a question for you. Did any of you solve this differently and get it right? Do you mind if I talk? Is that okay? So guys, Cody solved this problem in a really unique fashion. And actually, forgive me if it was kind of brilliant the way that he went at this. It was really insightful. Because what he did is made the connection back to the previous problem where you had to add up the masses. So basically what Cody was thinking was, add these together and that gives you the mass of the products. Then we already know the mass of one of the reactants because it's 5 grams. So if you add these up, that's the mass of the products. We know the mass of one of the reactants, so by subtracting those, the difference should give us the mass of the other should give us the mass of the other reactant just because of the law of conservation of mass. Kind of like the previous problem, part D. We couldn't get it to work, and I have no idea why. Did any of the rest of you try to solve it that way? I couldn't. Did you ever get it to work? I couldn't either, and I don't know why. And I fiddled with it a little bit yesterday, and then I thought to myself, what am I doing? It's the weekend. I don't want to work out. And then I quit. So, none of you got there? Okay. So guys, any other questions about the homework? Y'all good? Okay. So guys, here's how this goes. Why do we do homework? Radical thought. Ready? Not for points. I know. Public education is the constant pursuit not of learning but of points. We're going to change that. Guys, you do homework to expose yourself to a constantly changing collection of things that you've got to get good at. So guys, here's the deal. We don't grade homework in the traditional sense. I'm about to call your name. When I do, you're going to say yes or no. The question that you're answering is your homework done and do you now understand it? If you can say in good faith the answer is yes, tell me yes, points go in the book. If you tell me no, then guys, you have until the day of the test to go back and look at this stuff and make sure you understand it. Now understand guys, I know that that's leaving things in your court, and some of you are like, I still don't understand question 3, subset 4, subletter I, part Z. We're talking about the big idea. Do you now, did you get your questions answered? It's a spirit and not a letter of the law thing. Maybe a good way to think about it is this. Do you know you need to go back and revisit something because you still don't understand the idea? If the answer to that is yes, tell me no, because you still need to engage with this assignment. Because if you're done, just tell me yes. And that yes means that you can fairly put it in the collection of things that you now feel comfortable with, meaning we're ready to move on. So, guys, with that said, I do this publicly. This is not me showing everybody your grades. It's just this one assignment. And it goes like this. Sarah, you're good? Addie, how about you? Talmadge? Sarah? Bailey? Alice? Christian? No? McKenna? Jason? Emma? And Grayson? Daniel? Sage? Josh, you good? Okay. Jonah? Cody, you good? Robbie? Tucker? Ella, you good? Leah? Lise? Riley? And Caleb? Okay, I should make that a 0. Okay, so guys, that's it. We're done with that homework assignment. You can tuck it away. I'm going to put this away. And guys, you need to grab something you can take notes with and on. And we're going to get going. Did I take attendance? Oh, I did, because I got Hiram gone. Okay, so put this away. Grab this. Oh, never mind. So, yeah, good question. So guys, I'll never collect your binders, But if you're looking for organizational strategies, I would go class notes, homework, summaries, tests. So class notes, homework, chapter summaries, and then tests. But that's up to you. So guys, what we're going to do today is we're going to start into chapter 4. We are not going to get done with everything that, well, let me say this differently. Did any of you print the notes? You guys know you can, right? All of my notes are available online on our website. You can print them and you never have to take notes. Guys, we are not going to get done with everything that is in the notes. That is purposeful. I knew that we weren't. Because first of all, it's a short day, and also because invariably this first day of grading homework takes longer because there's lots of things that we need to get sorted out. So guys, we're not going to get done. What that will mean is as we're moving through the day, I'm going to be thinking in the back of my head about a logical stopping point. So when we get to that point, I'm just going to go, we're going to stop here. I'll show you the homework assignment with the understanding that you can't rightly do all of it, simply because we haven't covered all the material. But guys, with that said, do let me remind you that on Wednesday, in addition to the little bit of this homework that you can do, what else do you have due on Wednesday? Chapter 4 outline. Guys, I told you this, but let me reiterate. Why do we do chapter summaries? One, so you learn to learn from a textbook, because there's a name for that. It's called college. And the other reason that I do this is to give you points. Please don't make that hard for me. I want to give you points, but I can't if you don't turn stuff in. So guys, don't turn your chapter summaries in late. If you're not sure how to do it, let me know. I'd be happy to sit down with you. It's a lot like the way we talked about chapter 3 being organized as an outline. But guys, please turn this, it's the beginning of class on Wednesday. Yeah.
So the chapter 4, is it
Just outline it. And this will be the only time I will ask you to outline a chapter. It's one of many strategies, but I picked it because most of us know how to outline, so it's an easy place to start. So go ahead.
What do you want us to do with the solubility rules?
That's a good question, yeah, because there was another part to today's homework assignment, which was summarizing the solubility rules. We're not going to get to it today, I don't think. So we will break that out on Wednesday, because on Wednesday we'll get to precipitation reactions, and that's when we'll need it. Okay, are we settled and ready to go? Okay, so guys, grab your books and open up to the beginning of chapter 4. We are not going to frog march through this chapter like we did chapter 3. But guys, we are going to get started with it. And I know that we already talked about this, but I think it bears repeating. Guys, looking at the title for chapter 4, where is all of chapter 4 taking place? In water. So guys, this is the way we are going to start into this. We are going to start by talking about some terminology. Before we even talk about the kinds of reactions that happen in water, we've got to talk about how things behave when they go into water. Some of these terms you've heard and maybe are not quite clear on. Some of this is going to be completely new. But guys, it's critical that we create a common vocabulary before we get into the chemistry. So I think roughly this is how the day is going to break out. We're going to talk vocabulary today, and then I think at that point we're going to do a deep breath, call timeout, look at the homework, and just call it a day. Then we'll specifically get into precipitation reactions on Wednesday. Okay, so with that said, guys, the date today is the 26th. If you want to date your notes, you could make the title of this precipitation reactions. But guys, before we get to precipitation reactions, we've got to talk about some higher level stuff. Because this is all aqueous, the place that we need to start is right here. Guys, when we talk about aqueous reactions, we're talking about reactions that take place in water. In order to think about reactions that take place in water, we got to talk about how do things get into water. And it's at that point that we need to talk about solutions. So guys, this is not in the notes because I assume you understand it, but let's talk. What are the two parts of a solution? Solute and solvent. Which one is which? Salt water. Which is the salt? The solute, and the water is then the solvent. So guys, if you don't remember that, you can jot it down quickly, but those are terms that you need to have a working understanding of. Solute is the thing being dissolved. Solvent is the thing doing the dissolving. In the case of aqueous solutions, that means it's water. Okay, so guys, once we then understand that we're dissolving things in water, the first thing that you've got to understand is that this can happen in one of two ways. And we describe these processes based upon the behavior of the solutions that they make. One of these is what is called a non-electrolyte. So guys, functionally, and we'll dig into this more in a minute, but let me give this to you now. Guys, functionally, if a non-electrolyte dissolves in water, the solution that it forms does not conduct electricity. Did any of you ever know Mr. Miller or have siblings that had Miller for chemistry? He taught here 5 or 6 years ago, and he was like, well, he was nuts. He was a great guy, but he was crazy. And so he decided that he was going to make a solution testing device. And so literally what he did is he took a light, like a shop light, and he took the cord off of it, and he took one of the two wires that plugs into the wall, and he got a pair of scissors in there, and he cut it, and then stripped it back, and then chewed the ends off. So there were these two bare wires, and he would plug this thing into the wall, and then in front of his classes, he would shove those bare wires into solutions to see if they would light up. And then when he was done with it, many times he would just set it on his desk, still plugged in. Yeah, it was terrifying. But it did work. It actually did work. So there's better ways to do this. But guys, what then makes a solution a non-electrolyte? And guys, this is the thing that's confusing. When we have a substance that is a non-electrolyte, it does dissolve. And guys, I'm purposefully making this confusing. If you're sitting there going, wait, I don't understand what you're saying, you will. I want to give you the characteristics, and then we'll bring it together in a way that makes sense. So when solutions form, sometimes the thing that dissolves are what are called non-electrolytes. Do they dissolve? Yes. But what they don't do is conduct electricity. So now we need to have the conversation. For things to conduct electricity, what has to be present? What do you need for a substance to conduct electricity? You got to have things that are charged. Not quite. Let me show you. So you've got to have things that are charged. But guys, oh, this is going to be fun. We got to dehydrate our salt. It's really not, but it's still fun. So guys, table salt, that is this, right? Are the greens and grays charged? Yeah, sodium's +1, chlorine's -1. These things are charged. But does table salt conduct electricity in its solid form? Why not? What can't they do? Move. That's the ticket, guys. For something to conduct electricity, it has to meet two requirements. One, it has to be charged. Two, it has to be able to move. So this is charged, but can't move. We'll talk more about what happens when it dissolves in water. But for now, we're talking about non-electrolytes. And guys, when non-electrolytes dissolve in water, when something dissolves in water, can it now move around? Yeah, so why would a non-electrolyte not conduct electricity if it can move? What isn't it? It's not charged. And that's the point. Guys, when a non-electrolyte dissolves in water, it can now move. It just doesn't have a charge. As a result, it does not conduct electricity. Hi, how are you? Awesome. Okay. So guys, let's think about this. What are things in your experience that do dissolve in water, but when they do, the resulting solution does not conduct electricity? Yeah, sugar. Guys, sugar is a non-electrolyte. And I would encourage you to write it down as an example because it's nice to have a conceptual anchor. Do you know of others? I'll be impressed if you do. Things that dissolve in water but don't form ions. Yep, carbon dioxide dissolves in water. Carbonated water doesn't conduct electricity. Others? Alcohols dissolve in water but don't conduct electricity. Ooh, good question. And this is, you ready for this? Back up from that for a minute. Keep it in your brain, but don't think about it yet. So guys, these are the things that we talked about. I'm just going to do this. So C6H12O6, CO2, and CH3OH. These are all things that dissolve in water. Where are my pens? These are all things that dissolve in water but don't conduct electricity. What do they all have in common? And don't say carbon. No, yes, but no. What do they all have in common? They're all molecules. These are all non-metals bonded together. And remember, hydrogen is a metal, but it's freakishly strong and still forms covalent bonds. Guys, the idea is this. These are all molecules. So anytime a molecule dissolves in water, and we'll see this visually in a couple minutes, but anytime a molecule dissolves in water, it will be a non-electrolyte. Why? Because when it falls apart, it doesn't break into ions, it stays intact as molecules, and we'll see an animation of this in just a minute. So are we settled on that idea? Molecules, if they dissolve, they do not conduct electricity. They're non-electrolytes. Is that okay? Now to your point. HCl. What kind of bond exists inside of hydrochloric acid? And the answer is actually it's a molecule. HCl is a molecule. But when HCl dissolves in water, and actually all 7 of the strong acids, when a strong acid, and all 7 of the strong acids are molecular, they're all covalent bonds, when they dissolve in water, they actually form ions. They're molecules that form ions. The reason that it's different is because the ion that they release is hydrogen, and hydrogen is on that weird boundary between an ion and a covalent bond. And as a result, those are examples of molecules that are also electrolytes, but there aren't very many others. Is that okay? Okay, so guys, are you settled on non-electrolytes? Does that sit okay? Okay, so then let's talk about electrolytes. Not surprisingly, these are the opposite. Electrolytes also dissolve in water. The difference is that when electrolytes dissolve in water, they form ions. These ions then conduct electricity. So guys, give me a simple example of something that dissolves in water, and when it does, it breaks into ions. Salt, table salt. And guess what? All salts. If a salt dissolves in water, it will be an electrolyte. because when salts dissolve in water, the ionic bonds in the lattice break apart, and you end up with ions being released into solution. So when you spend $1 for that stupid bottle of Gatorade and it says it's an electrolyte sports drink, you realize what you just bought: salt water.
Why does that have so much sugar?
That's, well, and right. So it's not just salt, right? But does the sugar make it an electrolyte drink? See the point? Right. So the sugar doesn't make it an electrolyte. It's actually the salts that are dissolved in there. And it's not just sodium chloride. You can look it up. I don't remember what they are. But literally, when you buy an electrolyte sports drink, you're actually just paying for salt water. So why do we need the salts in the water? Because guys, in our body, do you understand this? In our body, these ions are actually neurotransmitters. And if we get depleted of these salts because we sweat, and you guys know this, if you've ever tasted your sweat, it tastes salty. When you're sweating, you are losing these ions, and if you lose enough of these ions, you actually have depleted amounts of these ions in your neurons, and your muscles start to short circuit because they're not getting proper communication through your neurons, and when your muscles short circuit, you cramp. So that's why we need these salt solutions, because they keep our neurons replenished with these ions that we need to pass signals from our brain to our muscles. So why do they put in sugar? Because we also need fuel. So long as we're drinking the salts, we may as well get the sugar too. But actually, like pro cyclists, a lot of the times will get their calories through different means, and they literally just drink salt water. I don't know how it's very dilute, or it'll make them throw up. But these guys are going through, I mean, it's crazy. After races, their kit is just white with sweat. So they can't get enough salt by drinking the electrolyte, because they drink so much sugar it makes them sick, that they'll actually eat salt. Yeah, that's crazy. So guys, do you understand the difference? Okay, so now this is important. Guys, I would encourage you to write this down. What do these things have in common? Electrolytes and non-electrolytes, what do they have in common? They all dissolve. So now we need to talk about another term. What is sand? Is sand an electrolyte or a non-electrolyte? Neither. It's non-soluble. So guys, understand there's a whole nother part to this conversation, which is stuff that just doesn't dissolve. Realize the things that we are talking about here all dissolve. They just behave differently when they dissolve. Do you see the distinction? Go ahead, Jason. Or are you just playing? You guys okay? Okay. So guys, let me show you then what this looks like. I don't know why it seems like this will be helpful, but we're going to do it. So guys, here we have sugar, and here we have salt. You'll notice, and I know you know this, but guys, both of these are white crystalline solids. But let's talk about this at a fundamental level, and it might help you understand the difference. So guys, salt first. If we could dig around super small guy size inside of salt, what would the salt look like? What have you seen before? This guy, right? So at the atomic level, this is what it looks like inside of salt. The gray is the sodium, the green is the chloride, and what are the sticks? Ionic bonds. So when a salt dissolves, the ionic bonds break, and the water molecules carry the ions off. There you've got free-moving ions, and they conduct. Okay. If you could see inside a crystal of sugar, what would it look like? Still like this. But here's the difference, and I'll show you a better representation in a minute. It's still a crystal, but what's the difference? Well, at each one of these points, what will we see? A sugar molecule. You'll have the C68, whatever sugar it is. You'll have a sugar molecule at each one of these points. So if that's the case, what are the sticks? Not ionic bonds. What holds sugar together? Intermolecular forces. Let's say that again. If this were a sugar molecule, each one of these points, if this were a sugar crystal, each one of these points would be a sugar molecule, and now the sticks would no longer be ionic bonds. They are intermolecular forces. Now, guys, think about this. What do you know about the strengths of intermolecular forces compared to bonds? Weaker or stronger? Intermolecular forces are weaker. As a result, what happens if you fill up a saucepan full of table salt and put it on a burner in a stove? What happens? Nothing. You can't melt salt at home. You can't get it hot enough. What happens if you take a saucepan full of sugar and put it on a stove? It melts. So why does this melt at such a lower temperature? What is breaking when sugar melts? IMFs. Covalent bonds? No. Where are the covalent bonds inside of a sugar? Inside the molecules. So when sugar melts, you're not breaking bonds, you're breaking IMFs. When salt melts, now you're breaking bonds. The same thing is true when they dissolve. When you dissolve a salt, you're breaking what kinds of forces? When you dissolve a salt, what kind of forces are breaking? Ionic bonds. When you dissolve a sugar, what kind of forces are breaking? Intermolecular forces. Okay, let me show this to you. This is pretty bad. Here it goes. In goes a cube. What could it be? Salt. Let's zoom in, shall we? Oh, yeah. Now, guys, this is then the trick. Why does salt dissolve in water? And the answer is because water molecules are bent and therefore polar. These polar water molecules act like little tugboats, grab a hold of the charged positive and negative chlorines, and literally rip them apart and carry them off into water. Now, guys, as this happens, notice, why is the oxygen pointing at the sodium but the hydrogen pointing at the chlorine? They're dipoles. Because, guys, remember, in a water molecule, water is a polar molecule. Water goes like this, and the oxygen is more electronegative than the hydrogen. So this is the positive and this is the negative dipole. So oxygen is the negative dipole pointing at the positive sodium. Hydrogen is the positive dipole pointing at the negative chloride. But these water molecules rip these guys apart and carry them off into solution. Now we have free charged particles, and salt water conducts electricity. Is this ringing true for you? So this is the Mr. Miller apparatus with nobody dying. Huh? Oh, wait. Oh. Is that weirdly satisfying? No, it's not. Okay, now, guys, same game, different players. In goes the cube, but now it's sugar. So, guys, when we zoom into this, what do you imagine you're going to see? Don't start packing up. When you get into this, what do you think you're going to see? It's going to be flat, right? They didn't try to go 3D. What are we going to see? Sugar molecules. And at each one of these points, we've got a sugar molecule. Now, guys, what are the forces that hold these molecules together? These sticks are IMFs. And so when this dissolves, will the carbons and the hydrogens and the oxygens come apart? No. These things leave as molecules. So, guys, why does sugar water not conduct electricity? Is it free? Yes, they're free. They're moving. But why doesn't it conduct? There's no charge. So when we take these and these things move off into solution, they are definitely dissolving. But they can't conduct because there's no charged particles. That's a good question. And the reason is this. If you could see a sugar, The sugar actually looks like this. It's CH2O, right? And we'll look at this more in depth later. But this molecule is wildly non-symmetrical. You've got an OH on one side of the carbon and an H on the other. And literally here, you've got a point of polarity, just like on a water molecule. And a water molecule is actually attracted to that point of polarity times as many carbon atoms as you've got. That's why these things dissolve so readily, because the polar water is attracted to the polar sugar. Does that make sense?
Yeah, but I thought the polarity is what made it charged, and so
No, so don't confuse polarity with charge. Polarity is a partial charge. Okay, so guys, let's do this. That is one long bell. So guys, hold on. You are more than welcome to look this up on your own if you'd like. But this is the homework.
And this is chapter 4, right?
This is chapter 4. Now, with that said, guys, it is the last slide of the slides that I posted. Guys, we are not going to grade any of this on Wednesday. I will answer questions on Wednesday, but we're going to dig in on Wednesday where we left off. Don't forget your chapter summaries. Have a lovely, do you guys know go to 4th period? Okay, have a great day, you guys. That's not a bug, that's a feature.